Hi, this week's episode of Crash Course Physics was concerned with simple harmonic motion, aka a mass on a spring. Now, this is a very basic physical system that appears in one form or another all over physics. And already I made a little mistake in this animation because, of course, the mass is not oscillating around the fixed point of the spring, because the spring cannot shrink to zero length, but you should think of it, well, as the way as they shown it in the video. That is, the mass is oscillating around the equilibrium point. Nevertheless, this is very similar to the pendulum that we've seen in an earlier video, where there's a constant exchange between kinetic and potential energy. Now, what kind of force creates such a motion? In fact, the force is always proportional to the displacement away from the equilibrium point and in opposite direction to it. So it always pulls the mass back to the equilibrium point. Now, how does this create this interchange between kinetic and potential energy? Well, if force is proportional to displacement, then the energy, the potential energy, is the area under a linear curve. So this is this 1/2 kx squared, in very much the same way as the relationship between momentum and velocity gave us the formula for kinetic energy. The sum of these two energy forms is always constant for this harmonic oscillator. Now, if only we had already seen a physical system where the acceleration of the particle is always proportional to the distance to a fixed point and opposite to it. Well, we've seen this in uniform linear motion. The acceleration vector was always pointing towards the origin and was always constant, that is proportional to the radius. And in this overlay, as they've also shown in the video, we see that the harmonic oscillator is just the projected one-dimensional version of uniform circular motion. To make this more precise, let's introduce coordinates, and you see that in the uniform linear motion, the x component of the acceleration is always proportional to the x component of the position. So this way we can actually exactly solve the equation of motion for the harmonic oscillator by noting that we are just projecting a uniform motion on the unit circle onto the x-axis, which is basic trigonometry. So the equation of motion is the amplitude, here the radius, times the cosine of angular velocity times time, and this is this familiar shape, a sinusoidal wave, and the period is 2 pi over omega, for example, or you can calculate all kinds of other properties of this curve. So that was all I wanted to share with you this week. Don't forget to subscribe if you haven't already, and I'm reasonably active on Twitter. See you next time.